So, today let's talk a little bit about units, dimensions, and make sure we've got an understanding of how conversion factors work, okay? Yes, I realize most of you have probably done this a few times, maybe a few hundred, 1,000 times, and that's okay. I've also found that sometimes people have explained to you ways that kind of work for unit conversion factors, but maybe nobody's ever really explained, here's the way that unit conversion factors work every single time, and here's why. Why do we make a big deal of that? Well, it's what I can tell you teaching courses like thermodynamics, fluid mechanics, subjects where about 80% of the mistakes you make are simply units mistakes. The units get really, really complicated, where most of probably what you've seen is pretty straightforward in terms of units. As you get a little further along, the units will get really complicated. And on top of that, because we're here in the United States, we've got to train you in both the English and the metric systems both, where the science classes, they get to they get it easy. They just teach you the metric system, and that's the one that makes sense. As engineers, we have to train you in both because you need to be able to function out in an industry that uses both. So let's talk a little bit about those today. And I remember one time teaching thermodynamics, one of my better students, sophomore, junior student, and I did something on the board, and the student looked at us like, why'd you do the units that way? And I explained, and they're like, oh yeah, I was just taught to always divide by the bigger number or something. It was like, just said something, it was like, whoa. Okay, so at the very least in an intro class, I'm gonna make sure that we talk about, just on a very basic level, make sure you've got a good fundamental understanding of why we do unit conversion factors the way we do them, and the different ways you can do them. To get there, we've got to understand what the heck are we trying to do with this. Now, and it's possible, it's perfectly fine if you have absolutely no idea what I'm talking about, because again, there's no requirement that you've had to have chemistry or physics or anything like that where we've formally taught you maybe how to do conversion factors. That's another reason I go ahead and do this at this point, is because it's not a requirement, and it's going to be helpful when you get into those other courses. But it's going to be infinitely helpful when you get into, again, some of the later engineering courses where we're really going to expect you've got a good understanding of those. Important question we've got to answer first: what is a dimension? What do you guys think? What is a dimension? And not looking ahead in the PowerPoints, those of you that maybe have already done that. What is a dimension? You guys will figure out very quickly. This is where I will stare at you with a blank stare until somebody gives me an answer that we can move forward with. What's a dimension?
Something that defines space.
Okay, something that defines space. Or planes, yeah. Okay, I like that. Any others? Those are types of dimensions. It's a little simpler than that. Right? And that's talking about, you guys are talking about trying to describe something or measure something, right? And a dimension's a little more broad than that. It doesn't just have to be what it sounds like. What you guys are talking about are thinking in terms of linear dimensions, length, and that's fine. Those are length is a dimension. Something we measure, that is a dimension. Time, for example, perfectly good example of a dimension. Temperature, something that we would measure. Now, more important question then, well, they're both honestly very important. But to our point today, what would you suggest as a unit? Yeah.
What you use to measure a dimension?
What you use to measure dimension. Exactly. Units measure dimensions. A unit A unit is a standardized quantity, a standard for measurement, a standard to measure dimension, or a physical quantity that needs clear definition in order to use it. Now, last time, when we talked about history of engineering, history of innovations, we said there were 4 factors that I point to that impeded innovations from occurring as rapidly as we see them occur today. Okay? What were those 4 factors?
Communication.
And it's not necessarily just communication, there's an adjective there. Go ahead. Doesn't work.
Fast communication.
Exactly. Right? Fast communication. Can you guys see that red, or do I need to use another color? You okay with that? Okay. That's okay. That's okay. I've got a green one up here, I think. No worries at all. Fast communication. There's a blue one up there. Blue one works. Absolutely. Fast communication. How's that? That good?
Yes, thank you.
You're very welcome. What else? We said there's 4.
Fear.
Lack of standardized unit of measurement.
Okay. Exactly. Lack of standards, we'll say. I heard fear. It's not just fear alone.
Fear that what you make will be used against you.
Yes. Fear of tech used against you. What was the 4th one?
Day-to-day tasks.
Day-to-day tasks. You can't specialize. You don't have people that become good engineers or good scientists if they've got to worry about how are they going to feed their family through the winter. Right? We need to be able to exchange what we're good at, and be able, in order to specialize, you've got to be able to know what you specialize in is going to provide for you and others. So these 4 slowed us down. Units is one of the ways we defeat this. Does us no good to be talking quickly if we're not talking the same language. Everybody in the world knows what a meter is. Even Americans have some idea, right? Everybody else in the world knows. If I tell anybody in the world that I'm about 1.8, 1.9 meters tall, they immediately know what that means, right? And Americans know, well, we can convert that to feet. No, very few of us think in meters unless you grew up somewhere else. Right? And it is what it is. So we talked about a few of these. What are some things we would normally measure? What are some things you would want to measure?
Dimensions of a room.
Okay, so those are going to boil down to length, right? You're talking about width and, yeah, so length, right? Volume, pressure.
Electricity.
Electricity, yes.
Time.
Perfect. What else?
Sound.
Yeah, these are some good ones. Alright. We could keep adding to this list as long as we wanted. But, I mean, just very quickly, you guys have been able to come up with some very good, simple things that we would want to measure. I always like to say, in a capitalist society, anything that we want to sell, we need to be able to measure, because we need to be able to communicate in a standard language. Once we've accomplished that, again, those are 2 big barriers that you've got to accomplish in order to allow innovations to occur and to occur rapidly. Okay. 4 base dimensions. Right? So you guys have given me several here. Volume, for example, is a combination of three lengths. Right? So I can break volume down into a base dimension of length. Pressure, which is force per unit area, and force can be broken down into mass, length, and time. Those of you who have had physics of any kind, we know that. The rest of you are going to learn that. Right? So all that to say is you have, a lot of times in science we refer to 7 base dimensions. And these are the 4 that we really worry about, everybody but those going into electricity. These are the 4 that we worry about in most of engineering and physics, especially at the beginning. Mass, length, and time. And then when we start talking about the thermal energies, we start talking about temperature. Okay? There is also light intensity, which we measure in a unit we call candela, or lumens. Right? That's another base dimension you can't derive from these other 4. I have to go back and look at what the others, there's 2 more that I just can't think of. Electrical charge. Electrical charge is a base dimension. And I think it's matter is the 7th one science typically refers to. But again, a lot of what we're going to do as engineers, unless you're dealing with electricity, we'll add electric charge here, are going to break down to these 4 base dimensions. And then again, we're talking about complex dimensions here in a little bit. Now, I think everybody's aware, right, and we kind of alluded to it here, that there are, we've got 2, or I've outright mentioned it, there's 2 main systems of units, especially here in the United States, that we've got to train engineers in. Now, if you've not had any kind of a science class, and looking at your assignment 1s, most of you have, and that's okay. That's not a requirement. Most of you have had some exposure to the SI system. Okay? And most people are aware that everybody everywhere else in the world uses a different set of units than we do. That's what we call the System International, or the SI system. And I'll give you just a quick crash course here in the SI system because it's not prerequisite knowledge for the course. But I'm not going to spend real long on it. And then what we as Americans typically call the English unit system, the rest of the world tends to call either the imperial system or the American customary system because it's us and just a few other places that still use it. Most of the world has gone ahead and converted almost entirely to the SI system. Again, just a quick crash course as to how the SI system works. You have your base units for different dimensions, and then we apply prefixes for if I need something larger or something smaller. Okay. Again, we said this is the meter. Okay. Roughly, in for those of us that think in inches and feet, it's roughly about 39.5 inches is a meter. And a lot of meter sticks will have inches, at least for here in the United States, a lot of our meter sticks will have inches on one side and centimeters on the other. Okay. Now, you wouldn't want to measure the distance that you drive today in meters. That would be a lot of meters that you would travel. You'd want to measure that in something larger. And so what we do is we apply prefixes to those base units to represent either larger or smaller quantities. The kilometer or kilometer, a kilo represents 1,000 of the base. So a kilometer is 1,000 meters. So again, there's these prefixes that we can apply to scale up or down the base units as we need. And I know this is a little too small for you to read. I'm not intending for you to read it. It's just to show you that there's a long list. If you just went and Googled SI prefixes and look at the images, you'll probably find something just like this. So it's there, it's available for you, but this is, again, I'm not expecting you to read this or copy any of this down. It's just something we can point to. Right? So again, to go smaller, you've got centa or centi, which means 100th. You've got deci and deca. Deci referring to 1/10, deca referring to 10 times. It's not too often you hear those used, but depending on what you're trying to measure and what the units are, it might make some sense. But centa is something we do hear a lot. anything you would measure in inches, normally you would measure in centimeters. You could measure it in millimeters, that's 1,000. So there's 1,000 millimeters in a meter. Going the other direction, normally you start at kilo. There is deca and hecto, meaning 10 and 100 respectively, but normally you start at kilo, meaning 1,000, mega, meaning a million, giga, meaning a billion, tera, meaning a trillion. And it's, especially today, most people are a lot more familiar with those terms than would have been 10, 15 years ago, because that's how we also measure storage. Computer storage and computer memory is measured in a similar fashion. So there's 1,000 bytes in a kilobyte, there's 1,000 kilobytes in a megabyte, or a million bytes in a megabyte. And a byte being a unit, a set number of ones and zeros, typically 8, that's grouped together to represent an amount of computer storage or computer memory. And so again, we measure those. Just one little block of ones and zeros is not enough information. We normally need thousands or millions of those. And today we're getting large enough, like this, the video I'm recording right now is going to be probably really close to a gigabyte when it's done, at 720 resolution. Okay. Now, and today you can start buying, we're not started. We have for the last several years been able to buy terabyte-sized drives, multiple terabyte-sized drives. I remember I'm not that old, and I remember our first computer my dad brought home when I was in middle school or high school, somewhere around in there, and we had a 2 gigabyte hard drive in that thing. Right? And I think it had a backup drive of 500 megabytes, so it had 2 hard drives, a primary and a backup. And I remember somebody asked when we were telling somebody about it, and they said, well, what do you need that much storage for? Right? And then what happened? Well, we figured out what to use that storage for, right? You give somebody tools and they're going to figure out what to use it for. Okay. So again, just a quick crash course on how the SI system works. You have base units, and then you go up or down depending on what you're trying to measure. So again, we mentioned several dimensions. We said there's 4 base dimensions: distance, time, temperature, and mass. Let's talk just a little bit about units there. So a unit being a standardized quantity we use to measure a particular dimension. A unit of length, most of us think in feet. Those of us growing up here in the United States, most of us think in feet or inches. As we mentioned several times, most of the rest of the world thinks in meters, kilometers, and centimeters. We also think in miles. Here in the United States, that's what we use to measure long distances. But humans have been trying to measure and communicate length so long as we've been humans trying to communicate, honestly. So what you'll find is you'll find a huge variety of different units of length, depending on what the application is. What are we using this for? So you get things like fathoms and furlongs and leagues. So there's just an infinite huge number of distance units, but just kind of a short list of some of the main ones that you might encounter. I can't remember the last time I encountered a league, but I've seen knots before, for example. Right? The unit of time. In both the English and the SI system, the base unit of time is the second. You can apply the SI prefixes in both unit sets to the second. Right? There's not a lot of standardized units outside of that. Now, when we start talking about quantities larger, lengths of time larger than a second, it's not uncommon in both unit sets that we'll go ahead and scale that up to some fraction of an Earth day or some fraction of an Earth year. But it's not to say you couldn't talk in terms of, say, megaseconds or gigaseconds. It's not typically used, but it's valid, it's accurate. But if we get to fractions of seconds, if we get to amount of length of time less than a second, it's not uncommon that we'll talk in milliseconds or microseconds or nanoseconds. Okay. We talked about 1 quadrillion calculations per second for computers today or more, meaning they're occurring in nano or femtoseconds there. Okay. We said length, time, and mass, and then temperature. All right. And by the way, one thing I should mention before I move into mass too far, let's talk about how these units are defined. All right. So the English system, you'd have to go back in the records and see. Typically, it's based off of, the foot would be based off the length of foot of the king, and then they realize that changes, and so they tried to standardize it. And the meter has been based on a number of things, right? One of the bases historically has been it's approximately the length of a pendulum that oscillates or repeats a cycle in 1 second. That, of course, means you have to have a definition of a second to define that, and that's also based on Earth's gravity, which could change, right? For a while there, it was based off of a length of latitude on Earth. We've had all these various bases that what is a meter over time, and you can go look that up if you want more information. Just something to point out. Today we use the distance that light will travel in a vacuum in a certain amount of seconds, a certain period of time. That's actually what we use today to define meters or some fraction of a meter. The reason we do that, why do we do that? Well, within our lifetime, probably everybody in this room, within our lifetime, the rotation of the Earth has changed. There was a massive volcanic eruption that actually altered Earth's spin. Right? Changed the momentum and actually slowed or sped the Earth up. So it's like fractions of a second. We don't even notice it. We haven't had to deal with it yet. It hasn't altered us enough to. There's not been enough years past that's altered us. But it does reemphasize that if you base these units off of something that could feasibly change, it's going to change. Right? It's over a long enough period of time. Something will happen to the Earth that will change that. Earth's gravity will change, Earth's size may change, the amount of time it takes for Earth to rotate about its axis, we have seen has changed. We watched a comet crash into Jupiter, and that's altered its behavior, okay? So there's all these... What we've done today is we said, instead of basing these units off, the SI units off of something that could change, we've tried to base them now off of things that will never change. And if we do encounter other life and we need to communicate how we measure things, we'd like some bases that they can use also that would make sense to them. Okay? So we do that with meter now. Again, it's based off of how far light will travel in a vacuum in a certain amount of time, meaning we have to define time first. So there's a definition of second. We've had a definition of a second for quite some time. It's based off of what we call atomic time. That's I believe it's the oscillation or the frequency at which cesium atoms oscillate or something. It has to do with phenomena that occurs on a molecular level that we can measure. We can measure repeatably and dependably. And it's a very, very accurate, it's the most accurate way we've found to keep track of time that never changes. All right. So now we've got a clear definition of a second, which allows us to have a clear definition of a meter that will never change. And when we talk about mass, another base dimension, mass. In the SI system, we'll use the gram as the base unit. A gram is a very small amount of matter. I should have borrowed from the physics guys or the chemistry guys just a gram. They're typically very, very small. A lot of times there's kind of this argument of, well, do we use the kilogram as the base unit or is the gram the base unit? Well, the gram's technically the base unit, but normally we use the kilogram kind of as the measure. The kilogram, and I know I need to actually read up on this. I know there was recently a big vote by some scientific body trying to decide on some definition of a gram or a kilogram that is always going to exist. I think they did that recently. I need to read up on that, okay? But up until this point, there's been basically a cylinder of, I believe it's a iridium platinum alloy cylinder in the SI Institute in France, where that thing is the kilogram. And that's what all of our bases of measurement is based upon. The problem with that is, just like every other object, it's collecting atomic and subatomic particles of radiation and cosmic dust, essentially. It's changing mass very, very slowly. We don't notice it. It's not measurable yet, but we know it will be eventually. And that's the reason there's a lot of efforts to base the unit of mass off of something that will never change. But right up until, again, unless they've changed it recently, it was this cylinder, and there's copies of it exist. The United States has one. There's various certified copies around that exist, but it all comes down to, well, what happens if somebody drops it and it nicks a little bit? And do we know what a kilogram is anymore? It's kind of dangerous to have it based off of something that will not always exist. In the English system, in the American customary system, we use pounds. Confusingly, we also use pounds for force. Whole other discussion that we'll get to have when you guys take me for thermodynamics or something like that. Sometimes there is the SI, or the English unit of slugs. What is a slug? I could look up what a slug is, but I don't think in slugs. But it's mathematically, it's kind of handy to use. It has its advantages over pounds. But anyway, we could talk all day. I could bore you with all kinds of details about units, and we could learn new things about units I don't know about. And I don't think that's probably what you guys want to do. We'll keep moving here. Okay. Temperature. What is temperature? Is kind of one of those. It's a little harder to measure. Whereas you can kind of experience length, you can experience mass. You can kind of experience time. You feel it passing. Temperature. What does that represent? Temperature basically represents the direction heat's going to flow. Heat's going to flow spontaneously from a higher temperature to a lower temperature. So if you're sitting in this room and you feel cold, what that means is you've got nerves in your body that are saying you're losing heat. Right? The environment you're in is at a lower temperature than you are, so you're losing heat to the environment. And if you feel really cold, that means your body's trying to tell you, hey, you're losing a lot of heat. We might need to do something different. Right? You either need to move, let's put some covering on, or let's get to buy a heat source. So how do we measure that? How do we measure the direction heat's going to spontaneously flow? Well, we've quantified that with temperature scales. Okay, now, those of us who've grown up in the States, most of us think in Fahrenheit. Most of the rest of the world thinks in Celsius. All right, so just like most of the other SI system units, it's kind of got a scientific basis. The Celsius scale, water boils at 100 degrees Celsius and it freezes at 0. In the Fahrenheit scale, I'm sure there's a reason, I'm not sure what it is, but water freezes at 32 for us and boils at 212. Again, why those values, I don't know. We could probably look it up, but they're not as obvious. Kelvin and Rankine, on the other hand. Kelvin and Rankine.
Professor,
Yes, ma'am.
don't they boil at different temperatures though based on pressure?
Yes.
So how does that, it changes, right?
Exactly. So Celsius is calibrated. It's water boils at 100 degrees Celsius at sea level, because you're right, based on pressure. What happens there is if you've got enough forces pushing molecules together, it's harder for them to boil, so they've got to go to a higher temperature. So if you go to a lower pressure or a higher pressure, you need a higher temperature to boil. You go to a lower pressure, so you go up in the atmosphere, so to Denver or somewhere. There's not as much forces pushing the molecules together into liquid form, so it can boil at a lower temperature. So yeah, you're exactly right. 100 Celsius, 212 Fahrenheit is the boiling point of water at approximately sea level.
At sea level, okay.
At sea level. Okay. Here in Oklahoma, we're actually a little bit above sea level. not by much. I know it seems flat here, but water does flow down to the Gulf from here, so we're actually above sea level here. So it wouldn't, I don't know what temperature, I've not measured it, but it would be a little less than 100 if you boil it here. It'd be close, but it would be a little less. There is these other two scales. If you've had chemistry and or physics, you've probably encountered Kelvin. Kelvin is what we call an absolute scale because there's a limit as to how low will the temperature go. That's called absolute zero. Kelvin does not have negative values, where Fahrenheit and Celsius, those will have negative values. So anything below the freezing point of water at 1 atmosphere is negative Celsius, and Fahrenheit, of course, occasionally we'll experience negative temperatures there. You do not experience negative values in the Kelvin scale. 0 Kelvin is the lowest possible temperature. That's the point where all molecular motion stops. You cannot remove any more heat at that point. It occurs, we've approached it really close in some crazy experiments on Earth. There's a documentary about, approaching zero. You get out in space, long distance away from any stars or black holes or anything else that's going to emit radiation. You could get pretty close to it. Rankine is also an absolute scale. It's the absolute scale in the English units. So 0 Kelvin and 0 Rankine are the same temperature. They both, Rankine and Kelvin, have no negative values. Now, if you've had chemistry before, you know to get from Kelvin to Celsius, it's a 273 degree difference. So 0 Kelvin is approximately minus 273 degrees Celsius. In Fahrenheit, it works the same way. To get from Rankine to Fahrenheit, it's a difference of about 460. So minus 460 degrees Fahrenheit, approximately, is absolute zero, or 0 Rankine. So to get from Rankine from Fahrenheit, you just add 460. It's the same way to get 2 Kelvin from Celsius, you would add 273. Why these particular values? Well, again, Celsius is calibrated so it boils at 100 in 1 atmosphere of pressure. Okay. The Rankine Fahrenheit scale, I don't know. We'd have to go look that up. Okay. All right. So again, not everything we want to measure. You guys have pointed several things out here that we can't just measure this. I can't just use length to measure this. I'm going to have multiple lengths to measure volume. Right? I can't just use length or mass or time to measure pressure. I'm going to need a combination of all three. So the different things we would measure that don't just fall into mass, length, and time and temperature categories, we've got to combine multiple dimensions. Okay? When you guys we talk pretty extensively about this in say, fluid mechanics, which is often kind of a late sophomore year, early junior year course for mechanical civil engineers. We talk extensively about dimensional analysis, right? And breaking things out into their base dimensions. Let's just mention it basically here, and let's point to some things that are pretty obvious that most of us can relate to. Just about all of you use speed or some kind of velocity if you drive a vehicle. Measure of distance over time. Again, one of the first quantities we'll introduce in physics will be, after we talk about motion, we'll talk about what causes motion. That's forces. Force is what we call mass times acceleration, or mass times distance per time squared. Okay? So there's not typically a base unit of speed in either the English or the SI system. It's normally whatever set of units makes sense, but basically any unit of length divided by any unit of time is a unit of speed. If I'm driving a car, it probably doesn't make sense to measure that in inches per day, right? That's not going to work, or inches per year, maybe, but probably not. But if I'm talking about continental drift, if I'm talking about how quickly is the coast of Japan approaching the coast of California, I'm not going to talk about that in miles per hour. That's too small of a number. I might talk about that in inches per year or centimeters per year. That's something that's it's approaching kind of a whole number, something that we can kind of relate to. So again, any of those are fine for speed. Just depends on what you're wanting to measure. Right? So with cars, normally we're going to measure that in miles or kilometers per hour because you're probably traveling a long distance with those. But honestly, I mean, we could talk about meters per second or feet per second when you're driving in a car. If you're driving short distances, that probably makes more sense. But if you're driving a longer distance, you probably want to have an idea how many hours it's going to take you to get there. And that's the reason we don't only measure car speeds in some long distance per hour. As I mentioned, you'll learn in physics about force, if you haven't already. Force being mass times acceleration. That's and so what that means is you can break down or convert any unit of force into some combination of a unit of mass, distance per time squared. Now, if you've not had physics and not required, you may be looking at that like, Steve, how do you square a second? How do you get time squared? That's acceleration measures the rate at which speed changes, right? Earth's gravity is about 9.8 meters per second squared, meaning for every second, if I drop an object, for every second that it drops, it's going to gain about 10 meters per second of speed for every second it drops. So it's changing. It's not a constant speed drop. It's increasing as it goes. It's accelerating. Force is the amount, what you have to apply to cause that change. Right? Now, the SI system, one of the major advantages of the SI system is everything's kind of related to these base units, and all of your base units for any dimension breaks down into a combination of 1 to 1 for the other base units. So since, again, force is mass times distance per time squared, 1 Newton, the unit of force in the SI system, breaks down to 1 kilogram times 1 meter divided by 1 second squared. And most SI units work this way. In the English system, it doesn't work that way. We have to learn specific conversion factors, but in the SI, a lot of them are 1 to 1. We use pounds in the English system. Most of us think in terms of weight. Weight is a type of force. It's the force gravity applies on an object. We think of weight in terms of pounds for most of us. You think about it in terms of newtons. You'd also think about it, as your mass. Your mass is what causes your weight. So you can a lot of other places they'll measure, instead of measuring your weight, they'll measure your mass. They'll tell you how many kilograms you have. Okay. All right. Just quickly here, I'd point this one out because we talk about area. There are some common units for area. Like if we're measuring land, here in the States we'll measure it in what we call acres. But if I wanted to measure the size of this room, I'd probably use square feet or square meters. Okay. Now an important thing, of course we know that 1 foot is 12 inches, right? 1 square foot is not 12 square inches. Very important there. 1 square foot is not 12 square inches. Let's look and see what that actually represents. If I've got 12 inches squared, I've got a square that's 12 inches on each side. That's 1 foot squared. Right? 1 square foot, this is a square, well, it's not scale, but roughly 1 square foot is 12 inches multiplied by 12 inches. That's 12 inches quantity squared. All right. Let me ask you something. If I've got 2x and I square that, is that 2x squared? No. What is it? It's 4x squared, right? I've got to square both things inside the parentheses. So this is 4 inches squared. I'm sorry, this is 4x squared. Same thing occurs here. What I want you to understand is because you are going to start plugging, well, sophomore year or so, you're going to start plugging units into your equations also. Treat the units just like they're an x. The difference here is let's say it's 12 meters, you know what a meter is. Whereas x represents some unknown quantity, a unit represents a quantity, it's just a known quantity. So you treat it just like it's a variable in algebra, and all the rules apply. Same thing in calculus, honestly. All the mathematical rules apply, just treat it just like it's a variable. It just happens to be a constant variable, which is an oxymoron. Questions here? Which is 144, right? 12 squared? 144 square inches is 1 foot squared. Okay. Not going to spend a lot of time here, but you'll encounter more and more complex dimensions. Electricity is basically energy or power, depending on whether you're measuring the rate at which you're delivering electricity or the rate at which you're consuming it, or you're measuring the total amount. And electricity is basically energy, and power is energy rate. It's energy per time. Okay? So the joule is the SI unit of energy. That's 1 joule is a Newton meter. Right? The watt, again, power. Watt is a unit of power. Power is an energy rate. Right? So if you know the number of watts, you don't know the energy. You just know the rate at which you're consuming energy. That's the reason we sell electricity in kilowatt hours. If I've consumed a kilowatt hour of electricity, I've used 1,000 watts for an entire hour. Right? There's some variation there. Okay. So a kilowatt hour is a kilowatt times an hour, and that gives you an amount of energy. The joule, of course, is the SI unit. The British thermal unit, the BTU, that's one of the few English units I can say has some scientific basis. The British thermal unit is the amount of energy required to increase the temperature of 1 pound of water 1 degree Fahrenheit. And the legend goes that James Watt figured out when he was feeding his steam engine coal, he figured out that the average horse could lift about 550 pounds of coal at a rate of 1 foot per second. So a horsepower is 550 foot-pounds per second. There are few conversion factors that I actually memorize, unless they've got a neat little story that goes along with them. So for some reason that one sticks out to me. All right. So like I said, we could talk way too long. I've probably already talked way too long about all the different units and where they came from and what they measure. Let's talk about what's really, really going to be useful for you moving forward. Make sure you've got a good foundation in how do you do conversion factors. Number one concept, every unit of measure has an equivalent value to another unit of the same type of measure. So every unit of length has an equivalent value to another unit of length. Every unit of mass is an equivalent value to another unit of mass, etc., etc. If it's the same dimension, there's going to be an equivalent value. Okay? How do we use that? Mathematically, what happens when you multiply by 1? Stays the same. All right? If I multiply a number by 1, I get the original number back. I think we call that the identity principle in algebra, right? Something like that. The number doesn't change. It stays the same. Okay. What do you think happens if I multiply a unit by 1?
You get 1 unit.
Yeah. It doesn't change. We get it back. Stays the same. If I take 1 meter, right, and I multiply it by 1, it's still a meter. I just get creative about what I call 1. right? So that's what we do when you conversion factors. You multiply by 1. How do we do that? Well, let's do the simple one, right? Because you guys will believe me on the simple one. We know 1 foot is 12 inches. We know that. That's the definition, okay? So what I'm saying by multiply by 1, solve for 1. So I said the first day, if I write an equation on the board and I move some things from one side of the equation to the other, that shouldn't be crazy for you. We got that? And like I said, treat your units just like it's an x, and all mathematical operations can take place. Okay? So if I've got 1x is equal to 12y, and I solve, basically move everything to one side of the equation, you can see what happens there. So I'm saying 1 foot divided by 12 inches is 1, because they're the same quantity. So if I divide them, I get 1. So, Steve, what the heck does this mean? Well, let's say that I've got something in inches, and I want to convert that to feet. So let's say I've got 36 inches, and I want to convert that to feet, right? So I set up a ratio, and this ratio just needs to equal 1. Because if I multiply by something that's 1, I don't change this. I might change the way it looks, but I've not changed the actual quantity, the actual value. So if I have inches in the numerator and I want to get rid of it, I need to multiply by something that has inches in the denominator. And so these then will cancel out. Don't let the mathematicians here say, we use the word cancel. They don't like that. But we know inches are non-zero, so it's okay for us. But anyway, that's another argument for another time. So I need to multiply by something that has inches in the denominator, feet in the numerator, and it's the same top and bottom, so it's 1. Well, we've got that. We know 1 foot is 12 inches. So now I'm multiplying 36 feet divided by 12, and that's simple. That's just 3. That's 3 feet. And that's really it. I mean, it's not, again, I've heard crazy things like, oh, you always divide by the big number. No, not necessarily, because we could also say, all right, if I go through, because I don't have it memorized off the top of my head, if I take the inverse of 12, I could just as easily say, right? Again, I need something that's got feet in the numerator and inches in the denominator. I could just as easily say that 1 inch is 0.0833 feet, and that's a true statement. And this is the same quantity top and bottom, because I just checked it on my calculator. I took 1 divided by 12, and this is what I get. And if I multiply this through, I'm still going to get 3. The inches are going to go away. I'm left with feet. You don't have to have 1 in the numerator, like you do here. Just as long as you have the same quantity in the denominator as you do the numerator, it doesn't matter what order you put them in, which one's 1. You don't have to divide by the bigger number always. In this case we do. It just depends on what you're trying to convert. It's more about what do you have and what do you want? What are you trying to convert to what? What do you have in the numerator that you're trying to get rid of? What do you have in the denominator that you're trying to get rid of? So let's go. Most people do pretty good with the simple one where you're just converting stuff out of the numerator. Let's talk about what happens when I've got stuff in the numerator and the denominator. All right, so if we talk about speed, we talk about 60 miles per hour. All right, 60 miles per hour is the same as saying I'm traveling 60 miles for every hour. 60 miles divided by an hour. Okay? Now, how do I go from here? I want to go from here to feet per second. How do I do that? Well, I've got to convert both the miles and the hours. So what do I need? I need some equivalent of miles to feet. I need some equivalent of hours to seconds. Well, there's 60 minutes in an hour, and then there's 60 seconds in a minute. So 60 squared is 3,600. Okay. There's 3,600 seconds for every hour. And by definition of a mile, that's 5,280, 5,280 feet. That's not one I expect you to have memorized. Now, if you don't have 3,600 memorized, that's okay. You can get there. Nothing saying you couldn't convert to minutes first and then seconds second. Second. That's fine. So how do we do that? Well, again, it comes down to be careful trying to memorize, do this and do that always. No. Think more about it. And this is one place we start asking you to think like an engineer. Think more about what do you have, what do you want, and how can you get there. All right? So what do I have? I have miles in the numerator. What do I want? I want feet in the denominator. So I need to multiply by something because I've got miles in the numerator, so I need to put miles in the denominator there. And I want feet in the numerator, so I've got to multiply by something with feet in the numerator to get what I want. So let's convert the length first, and then we convert the time, or vice versa. Let's convert them one at a time, okay? So again, we've already said, well, for every mile, there's 5,280 feet. And then, because I have hours in the denominator, and I would like seconds in the denominator, so I need to, again, what do you have? What do you want? I want to get rid of hours and go to seconds in the denominator. So I need to multiply by something that has hours in the numerator to get rid of the hours, seconds in the denominator. And then I just need the values here. So I know 1 hour is 3,600 seconds. There's nothing saying I couldn't say, well, 1 second is what fraction of an hour, and plug that in, and that works just fine. Okay. Excuse me. And then you run this through. You run this through through a calculator. Again, your hours are going to cancel out. You can see that there. Your miles are going to cancel out. Same top and bottom, and it's non-zero. So 60 times 5,280 feet divided by 3,600 seconds. And when you run that through a calculator, you should get something like 88 feet per second. So if you're traveling, keep that in mind when you're driving down the road and you've got your cell phone up. For every second at 60 miles per hour, let's see, these tiles are a little bigger than 1 foot, so let's make it easy. Let's say they're a foot, so this is 4, and this is 1, 2, 3, 4, so it's 4 for every dark line. 4, 8, 12, 16, 20, 24, 28, 32, we're not 40 foot in this room, 35 foot length of this room, 88 feet per second. Somewhere between 2 and 3 lengths of this room every second at 60 miles an hour. If you're driving faster than that, you're moving 3 to 4 lengths of this room every second when you're traveling at highway speeds. Okay? Again, please be careful with your phone and not the road. That's important. That's really important. Hopefully this kind of helps drive that home. But again, be careful memorizing things. One thing you want to memorize here is what do you have, what do you want, how can I get there? That mantra is going to serve you in many lines of work, but especially in engineering. What do I have in the denominator? What do I want in the denominator? Multiply by something that does that for me. Okay? Questions for me? Let's do 2 things before I turn you loose. First and foremost, when you go to Canvas, there's an assignment here to limit the exposure on both of us. I'm just going to have you submit it on PDF. If you have trouble getting a PDF, or you could submit JPEGs also, that would be okay. When you go into Canvas, you can go into modules or assignments. In either place, you should see assignment 3, unit conversion factors. Pull that up. I've got a document in there that's got, I've got some instructions for you there. You know, again, there's a place here you can upload a file. If you're struggling with any of this, come see me. Let's make sure we get you the help in Canvas you need. But what I would suggest is just work these out on paper, by hand on paper, and then just take a picture and or scan it to a PDF using your device. Okay? There's some instructions here. Read through the document. But basically, I've got 8 conversion factors I'm asking you to do down here. And when you read through here, it's going to say, hey, by the way, numbers 5 through 8, you probably want to do in multiple steps. Because what happens is if you mess something up and you don't have a lot of algebra there, or you haven't shown me the steps you're going through to make the conversion, you mess it up, it's wrong, like completely wrong. If you show me how you did the conversions and you just happen to flip this one over, all right, that's like, you know, that's like a fourth of the credit on that problem. That's not that big a deal. That's a simple mistake. But if you just say, well, 60 mile per hour is equal to 88 feet per second, and if you got it wrong, I have to count the whole thing off. Does that make sense?
Mm-hmm.
We clear on that? Okay. So, again, the first 4 you can probably just simply say, well, 4,000 seconds is this many hours, or 400,000 seconds is this many hours. Okay, that's fine. But when we get into, all right, what about slugs per minute converting to kilograms per hour, or whatever I'm asking you to do there, the more steps you show me, the easier it is to grade. And that also shows me you understand, which is really what I'm after. Okay. Okay, I'm going to stop the video because I'm going to take roll, and the world doesn't need